So at the top of page 60, we're now talking about position, velocity, and acceleration problems. And unless we're working with an object or a particle moving along the x-axis or the y-axis, we will often use the letter S to represent position. So S of t is typically position. And so we recall already, hopefully, that the first derivative of position is velocity. So if I were to integrate a velocity function, what I would get is a position function plus c. I can't forget about my constant of integration. We also know that the second derivative of position is the first derivative of velocity, which is acceleration. And that if I integrate my acceleration function, I should get a velocity function plus some constant of integration. So if we're thinking about it, when I integrate velocity between two particular values, so if I were to integrate v from a to b, what I'm getting is the change in position. In fact, more generally, anytime I integrate a derivative, so like let's say I integrate f prime of x from a to b, what this tells me is this gives me the change in f of x from a to b. And I know that because that's the first fundamental theorem of calculus, right? This gives me f of b minus f of a. So it's really critical that when we're talking about the change in position, that we call that displacement. So that is our change in position. Now that is different from total distance traveled. So imagine that you are somebody who walks to school and you live exactly 1 mile from Eagle Crest. So here's your house and here's EHS, really artistic. So let's say in the morning you walk 1 mile to school, and then in the afternoon you walk 1 mile back, and we're not considering any other walking that you did during the day. So at the end of the day, your displacement from your home is 0, because it's like you went 1 mile in one direction and came 1 mile back. But your total distance traveled from your home to Eagle Crest and back would be 2 miles. So total distance traveled, we find that by integrating the absolute value of velocity. And the absolute value of velocity, just more generally, that's what we think of when we say the word speed. So we know with velocity, the sign matters because that has to do with the direction of our change in position. But when we talk about speed, like if I'm looking at my speedometer in the car, I don't get a negative speed when I'm going a different direction. I just have a speed. So speed does not have a sign. So that is our absolute value of velocity. And when we integrate that, that gives us our total distance traveled. So it's really critical that we understand the difference between displacement and total distance traveled, and that we are careful when we read questions that could be about either or both of those things. So if I wanted to find the position of a function in the future, like at some future time, what I could think about is I could think about my starting position. Sometimes I call this like an initial condition because it doesn't have to be, let me see if I can spell the word initial. I'm just going to write IC, an initial condition. This doesn't have to be like S of 0. This doesn't have to be our position at time equals 0. It's just some position that we know. And if I add to that my displacement from where I started to where I'm going, so that's going to be my t. So like t is representing the time at which I'm trying to find my position. I would get this formula here, and we could write this as an accumulation function. I can also just fill in the values that I'm looking for. And then finally, our average velocity. Well, we learned already that the average value of a function, that we integrate that function and then essentially divide by our difference in limits. But remember that when we integrate velocity, we find our displacement. So when we integrate velocity, it's like we would find S of B minus S of A. And then if I wanted to make this my average velocity or my average change of my displacement, I would divide by b over a, right? That's average rate of change. So these are the same thing. Like if I take this integral and I actually find the antiderivative and then multiply by 1 over b minus a, what I get is my average rate of change of position. And that is the same as my average value of velocity. So we could use those interchangeably, but sometimes we have information to use one versus the other, but those are equivalent statements there. All right, let's consider this example where an object is moving along the x-axis. At time t equals 5, the object is at a position of x equals 3. So because we're calling this x, I'm going to think of my function as x of t, not s of t. So this is going to be my position function. And what we're being given is that x of 5 equals 3. So again, I can consider this like an initial condition, even though it's not x of 0. We're also told that the velocity is shown below in the graph. So our graph is velocity in presumably feet per second. So the first question we're asked is, when is the object traveling to the left? So remember, the sign of velocity tells us the direction in which we are traveling. And I know I'm going to consider down or left to be a negative direction, because if I think on my x-axis, if I'm moving to the left, my position is decreasing. So what I'm really looking for here is where v of t is negative. So the object is traveling to the left on the interval from 5 to 8. I could say like t is less than 8 but is greater than 5, or I could say the interval from 5 to 8. So the object is traveling, that was the word is, to the left on the interval 5 to 8 because velocity, so v of t is negative. Velocity is less than 0. Next, we're asked for the speed of the object at t equals 6. So remember, we said speed is the absolute value of velocity. So what we're looking for is the absolute value of v of 6. And so if I look on my graph, v of 6 is negative 2, and the absolute value of negative 2 is 2. So going back to this, since we do have units on this problem, we should include our units there. So our velocity is measured in feet per second. All right, what is the displacement of the object between t equals 0 and t equals 10? And for displacement, I don't have to consider the initial position or anything. It doesn't matter what my position was at, in this case, t equals 5. We know our position was 3. I just need to know between 0 and 10, from t equals 0 to t equals 10, how far am I displaced from where I was at t equals 0? So again, if we are finding our displacement, that's just our change in position. So we want to integrate from 0 to 10 our velocity function. All right, so using our graph, I like to just break this up into easy shapes. So I've got, let's see, a rectangle here, that's 3 by 4. A triangle here, that's 2 by 4, so that has an area of 4. A triangle down here, that is going to have an area of 3. And then this little triangle has an area of 2. So if I'm finding my displacement, the signs matter. So I'm going to add 12 plus 4 plus negative 3, because that area below the x-axis there is negative, plus 2, and I end up getting 15 feet. So I want to point out something important here if we consider our units. When we measured velocity, we said velocity was measured in feet per second. And remember, we said this dt, that this is not just like an ornament, it's not decorative, that this represents our delta t. This represents the differential of t. It's like delta t if delta t is infinitesimally small. So this number is almost zero, but not exactly zero. And so when we multiply this by this has units. Our units here is what time is measured in, which is in seconds. So we know when we do that multiplication, the units I'm left with are just feet. So if I integrate velocity with respect to time, I multiply the units of velocity times the units of time to get my units feet. All right, finally, in part D, well, actually not finally, because this problem goes on to the next page, but in part D, we were asked, what is the total distance traveled by the object between 0 and t? So this is really similar to what we did above, but we said to find total distance traveled, we need the absolute value of the velocity. So if I look at my graph again, the only thing that changes is what was a -3 when I found my displacement. I'm going to now think of that as a +3. And if I were to actually graph this absolute value function, it would just flip that little triangle up over the axis. So I'm going to add 12 plus 4 plus +3 plus 2, and that is going to give me 21 feet. In part E, we're asked, what is the position of the object at t equals 10? So this is asking us for a specific position, and it's now important that we recall that we were given, and AP usually doesn't give us information we don't need. So it's important that we were told the position at t equals 5 is 3. Because to find my future position, I want to start at the position that I know, which is my position at t equals 5, which is 3, and I want to add to that my displacement from 5 to, or in this case, 10. So from t equals 5 to t equals whatever. So we could write this as an accumulation function. That's how it's written in the box at the top of page 60. I could think of this as my position at any time t is going to be my position at 5 plus the displacement from 5 to whatever t is of our velocity. And remember that, you know what, I shouldn't use x. Let me call this something else. I'm going to say vy dy. So those y's right there are dummy variables. And again, I could use any letter I want. I just shouldn't use x because x is already a variable in this problem. Now, we don't have to write an accumulation function because what we're really finding here is x of 10. So x of 10, now I could just plug that in to my accumulation function. X of 10, our position at 10, is going to be x of 5 plus the definite integral from 5 to 10 of v of t dt. So again, as soon as I get rid of my limit of integration as a variable, I can replace my dummy variable with my true variable of integration, which is t. All right, so we said we know that our position, x of 5, is equal to 3. So when I add to that my displacement, my change in position from 5 to 10, let's see, I'm adding a -3 and a +2. So I'm just adding this area and this area. All right, so I have 3 plus -3 plus 2. So we know our position at t equals 10 is just 2. All right, finally, what is the acceleration of the object at t equals 4? And remember, acceleration is the first derivative of velocity. So what I'm finding is my acceleration at 4. And since I have a graph of velocity to look at, if I go to where t equals 4, the derivative there is just going to be the slope. Since this is linear, just the slope of this piece. We know derivative is the slope of our function or the slope of its tangent line, but when our piece is linear, our derivative is just our slope. So if I find my slope, I'm going to use this point and this point. Actually, I could use this point and my point on the x-axis. I'm going to go down 4, right, 2. So my slope is just -4 over 2, which is just negative 2. So negative 2 feet per second per second. And you can say, you could say negative 2 feet per second squared. Oops.